All right, let's get it. Chapter 3. So let's recap for a second where we are. We've got a Python program that can recognize handwritten digits. After about 30 seconds of training, it can do 95% accuracy. Actually, it looks like after 13 seconds it was able to do 95% accuracy, but it's going to keep improving for a little bit. It's kind of plateaued around 95. It's going up and down and up and down. The amount that it goes up is pretty random. Oh, one sec, I'm not sharing my screen. So let me do that one more time. Yeah, so we jumped to 90% after 1 second, and then after 10 more seconds we get to 95, and then we stay around 95 for the rest of the 30 seconds. So today we're going to be learning some improvements that we can make. What we've done so far is just a very straightforward sigmoid neurons, backpropagation, quadratic cost function, and the one optimization we have here is that we're doing multiple examples at the same time within a mini batch by doing matrix operations instead of vector operations. Which yielded about a 3x improvement in speed, not in quality. So let's get going. Chapter 3, improving the way neural networks learn. When a golf player is first learning to play golf, they usually spend most of their time developing a basic swing. Only gradually do they develop other shots, learning to chip, draw, and fade the ball, building on and modifying their basic swing. In a similar way, up to now we've focused on understanding the backpropagation algorithm. It's our basic swing, the foundation for learning in most work on neural networks. In this chapter, I explain a suite of techniques that can be used to improve on our vanilla implementation of backpropagation, and so improve the way our networks learn. The techniques we'll develop in this chapter include a better choice of cost function, known as the cross-entropy cost function, 4 so-called regularization methods, L1 and L2 regularization, dropout, and artificial expansion of the training data, which make our networks better at generalizing beyond the training data, a better method for initializing the weights in the network, and a set of heuristics to help choose good hyperparameters for the network. I'll also overview several other techniques in less depth. The discussions are largely independent of one another, and so you may jump ahead if you wish. We'll also implement many of the techniques in running code and use them to improve the results obtained in the handwriting classification problem studied in Chapter 1. Of course, we're only covering a few of the many techniques which have been developed for use in neural nets. The philosophy is that the best entree to the plethora of available techniques is in-depth study of a few of the most important. Mastering those important techniques is not just useful in its own right, but will also deepen your understanding of what problems can arise when you use neural networks. That will leave you well prepared to quickly pick up other techniques as you need them. Cross-entropy cost function. Most of us find it unpleasant to be wrong. Soon after beginning to learn the piano, I gave my first performance before an audience. I was nervous and began playing the piece an octave too low. I got confused and couldn't continue until someone pointed out my error. I was very embarrassed, yet while unpleasant, we also learn quickly when we're decisively wrong. You can bet that the next time I played for an audience, I played in the correct octave. By contrast, we learn more slowly when our errors are less well defined. Ideally, we hope and expect that our neural networks will learn fast from their errors. Is this what happens in practice? To answer this question, let's look at a toy example. The example involves a neuron with just one input, weight, bias, output. We'll train this neuron to do something ridiculously easy. Take the input 1 to the output 0. Of course, this is such a trivial task that we could easily figure out an appropriate weight and bias by hand without using a learning algorithm. However, it turns out to be illuminating to use gradient descent to attempt to learn a weight and bias. So let's look at how the neuron learns. To make things definite, I'll pick the initial weight to be 0.6 and the initial bias to be 0.9. These are generic choices used as a place to begin learning. I wasn't picking them to be special in any way. The initial output from the neuron is 0.82, so quite a bit of learning will be needed before our neuron gets near the desired output 8.0. Click Run in the bottom right corner below to see how the neuron learns an output much closer to 0.0. Click Run. Ooh. Okay. So the cost goes down over time. It never gets all the way to the best output. And it kind of slows down once it gets a certain amount of the way there. Note that this isn't a pre-recorded animation. Your browser is actually computing the gradient, then using the gradient to update the weight and bias and displaying the result. The learning rate is eta equals 0.15, which turns out to be slow enough that we can follow what's happening, but fast enough that we can get substantial learning in just a few seconds. The cost is the quadratic function c, cost function c, introduced back in chapter 1. I'll remind you of the exact form of the cost function shortly, so there's no need to go and dig up the definition. Note that you can run the animation multiple times by clicking on Run again. As you can see, the neuron rapidly learns a weight and bias that drives down the cost and gives an output from the neuron of about 0.09. That's not quite the desired output 0.0, but it is pretty good. Suppose, however, that we instead choose both the starting weight and the starting bias to be 2.0. In this case, the initial output is 0.98, which is very badly wrong. Let's look at how the neuron learns to output 0 in this case. Click Run again. So it takes a really long time before it starts to plateau, or before it starts to dip. And I'm guessing this is because of a thing that we learned in a previous chapter, which is that neurons that are close to saturation and that have, like neurons that are outputting a number close to 1 and close to 0 don't learn very much. Although this example uses the same learning rate, eta equals 0.15, we can see that learning starts out much more slowly. Indeed, the first 150 or so learning epochs, the weight and biases don't change that much. Then the learning kicks in, and much as in our first example, the neuron's output rapidly moves closer to 0. This behavior is strange when contrasted to human learning. As I said in the beginning of this section, we often learn fastest when we're badly wrong about something, but we've just seen that our artificial neuron has a lot of difficulty learning when it's badly wrong. Far more difficulty than when it's just a little wrong. What's more, it turns out that this behavior occurs not just in this toy model, but in more general networks. Why is learning so slow, and can we find a way of avoiding this slowdown? To understand the origin of the problem, consider that our neuron learns by changing the weight and bias at a rate determined by the partial derivatives of the cost function, derivative of c with respect to w and derivative of c with respect to b. So saying learning is slow is really the same as saying that those partial derivatives are small. The challenge is to understand why they are small. To understand that, let's compute the partial derivatives. Recall that we're using the quadratic cost function, which from equation 6 is given by c equals the difference between what we wanted and what we got squared over 2, where a is the neuron's output, where the training input x equals 1 is used, and y equals 0 is the corresponding desired output. To write this more explicitly in terms of the weights and bias, recall that a equals sigmoid of z, where z equals wx plus b. Using the chain rule to differentiate with respect to the weight and bias, we get derivative of c with respect to w is equal to I guess because x is 1, it drops out. The derivative with respect to w and b is the same, and it's activation times sigmoid prime of z. where I've substituted x equals 1 and y equals 0. To understand the behavior of these expressions, let's look more closely at the sigmoid prime of z term on the right-hand side. Recall the shape of the sigmoid function. We can see from the graph that the neuron's output is close to 1, the curve gets very flat, and so sigmoid prime of z gets very small. Equations 55 and 56 then tell us that derivative of c with respect to w and b get very small. This is the origin of the learning slowdown. What's more, as we shall see a little later, the learning slowdown occurs for essentially the same reason in more general neural networks, not just the toy example we've been playing with. Introducing the cross-entropy cost function. How can we address the learning slowdown? It turns out that we can solve the problem by replacing the quadratic cost with a different cost function known as the cross-entropy. To understand the cross-entropy, let's move a little away from our super simple toy model. We'll suppose instead that we're trying to train a neuron with several input variables, x1, x2, etc., corresponding weights, w1, w2, etc., and a bias b. The output from the neuron is, of course, activation equals sigmoid of z, where z equals the sum of the products of the w's and x's plus b is the weighted sum of the inputs. We define the cross-entropy function, cost function for this neuron by c is equal to negative 1 over n times the sum over x being the inputs, of y log ln of a plus 1 minus y times ln of 1 minus a, where n is the total number of inputs of training data, items of training data, the sum over all training inputs x, and y is the corresponding desired output. It's not obvious that the expression 57 fixes the learning slowdown problem. In fact, frankly, it's not even obvious that it makes sense to call this a cost function. Before addressing the learning slowdown, let's see in what sense the cross-entropy can be interpreted as a cost function. Two properties in particular make it reasonable to interpret the cross-entropy as a cost function. First, it's non-negative, that is, c is greater than 0. To see this, notice that a, all the individual terms in the sum 57 are negative, since both logarithms are of numbers in the range 0 to 1, and b, there is a minus sign in front of the sum. So a the a is a number between 0 and 1 if you're using sigmoid, because then your output is always between 0 and 1. If you're using a different activation function, a or ln of a might not be negative. What does ln of a look like? So it looks like it's undefined less than 0. It's negative less than 1, and it's positive greater than 1. Okay, so I guess that means you can't even use cross-entropy if your neurons can output numbers that are negative, because this part would be undefined. Maybe it becomes defined when you do the whole thing somehow. And you can do it when your activation function can give numbers greater than 1. But this part won't necessarily be negative, which might not matter. And then 1 minus a, I guess similarly, if this is numbers between 0 and 1, then this will be negative. If this could be any positive numbers, then this becomes not defined. Okay. But for sigmoid, everything he's saying here makes sense. But I'm not sure how it's going to make sense for ReLUs. Second, if the neuron's actual output is close to the desired output for all training inputs x, then the cross entropy will be close to 0. Footnote. To prove this, I will need to assume that the desired outputs y are all either 0 or 1. This is usually the case when solving classification problems, for example, or when computing Boolean functions. To understand what happens when we don't make this assumption, see the exercises at the end of this section. Oh boy, sounds like a mathy exercise we're going to be asked to do. To see this, suppose that, for example, y equals 0 and the activation is about equal to 0 for some input x. This is a case when the neuron is doing a good job on that input. We see that while the first term in the expression, 57, for the cost vanishes, since y equals 0, while the second... let me actually look at the equation. The neuron's actual output is close to the desired output. That would mean A is equal to Y. And then we're going to try Y is 0 and we're going to try Y is 1. So if y is 0, then you get negative infinity here, basically. Plus 1 times log of 1 is just 1. So you get like negative infinity, and then this becomes you negate it, so you get like infinity. We see that the first term in the expression for the cost vanishes since y equals 0. Wait, I said negative infinity and they said, oh, because the y in front. Okay. I don't know. So yeah, it's like negative infinity times 0. And the second term becomes 0. A similar analysis holds when y equals 1 and a is approximately equal to 1. So when y equals 1, you get log of 1, which is 0, plus 1 minus 1, so that's 0 times something, and we're just going to ignore the something, I guess. And so the contribution to the cost will be low provided the actual output is close to the desired output. Summing up, the cross entropy is positive and tends towards 0 as the neuron gets better at computing the desired output y for all training inputs x. These are both properties we'd intuitively expect for a cost function. Indeed, both properties are also satisfied by the quadratic cost, so that's good news for the cross entropy. But the cross entropy cost function has the benefit that, unlike the quadratic cost, it avoids the problem of learning slowing down. To see this, let's compute the partial derivative of the cross entropy cost with respect to the weights. We substitute A equals sigmoid of Z into 57 and apply the chain rule twice. Compute the partial derivative of the cross entropy cost with respect to the weights. Okay. So A just became sigmoid of Z, and then we're taking the derivative with respect to W of this. Why do we have y over a? Where did the logs go? Maybe that's because we already took the derivative. derivative of ln of x is 1 over x. So I'm guessing we have y times ln of a. So a is equal to sigmoid of z. We're gonna take the derivative of c with respect to w. And then by doing the chain rule, we're gonna say that's the same as derivative of this with respect to a times derivative of a with respect to w. So that's how you ended up with y over a. Yeah, okay. All right, we're learning how to do chain rules. So yeah, you end up with this thing that I'm not going to read out loud. Putting everything over a common denominator and simplifying, this becomes derivative of c with respect to w equals this big thing. Using the definition of the sigmoid function, sigmoid of z equals 1 over 1 plus e to the negative z. And a little algebra, we can show that sigmoid prime of z equals sigmoid of z times 1 minus sigmoid of z. So this is the definition that we're already using in our implementation of sigmoid prime. I'll ask you to verify this in an exercise below. I don't know if I'm going to do these like very mathy exercises. It's not really what I'm trying to learn here. But for now, let's accept it as given. We see that sigmoid prime of z and sigmoid of z times 1 minus sigmoid of z terms cancel in the equation just above. Yeah, because this is the same as this. And it simplifies to become 1 over n times sum over x of xj times sigmoid of z minus y. This is a beautiful expression. It tells us that the rate at which the weight learns is controlled by sigmoid of z minus y, i.e. the error in the output. The larger the error, the faster the neuron will learn. This is just what we'd intuitively expect. In particular, it avoids the learning slowdown caused by the sigmoid prime of z term in the analogous equation for the quadratic cost, equation 55. When we use the cross entropy, the sigmoid prime of z term gets cancelled out and we no longer need to worry about it being small. This cancellation is the special miracle ensured by the cross entropy cost function. Actually, it's not really a miracle. As we'll see later, the cross entropy was specially chosen to have just this property. In a similar way, we can compute the partial derivative for the bias. I won't go through all the details again, but you can easily verify that derivative of c with respect to b is equal to the same thing, but you don't multiply x. I'm just curious, in our implementation, where did the cost function fit in? So you've got derivative of the cost function with respect to x was x minus y for us before. Then we had delta L, which was equal to what was it equal to? It was equal to the derivative with respect to z. So derivative of c with respect to x would need to change with a different cost function. But I guess we'd have to pull up BP1 to BP4 again and just see where the cost function fits in. Alright. Again, this avoids the learning slowdown caused by the sigmoid prime times z term in the analogous equation for the quadratic cost. So, equation 56 and equation 55. So these were the old things we were doing, and they had a sigmoid prime in it, and that was the problem. So the sigmoid prime's coming from here and coming from here. You know what's really interesting is I was saying one of the things I wanted to try earlier was to just get rid of the sigmoid prime and see if it still works. I think that was an exercise or something, and it didn't work. But shouldn't it work according to this? Oh, it is. It's kind of working. It's not working as well. But it's definitely working. The times x thing is confusing. I don't remember doing that part. Let's bring the sigmoid primes back here. Yeah, I don't know. I guess I'm a little confused. If this is what we're doing right now, activation times sigmoid prime of z is the derivative with respect to the w. And the new thing is the new thing still has an x. It doesn't have the sigmoid prime. Apart from not having the sigmoid prime, it's the same. It's just you get rid of the sigmoid prime. A of z is the same as a, or sigmoid of z is the same as a. So for the weights, you should just get rid of the sigmoid prime. For the biases, you should just get rid of the sigmoid prime. Why does a minus y become just a? I'm not sure. But if before what we were doing was a minus y times sigmoid prime, and after we should just be doing a minus y, then just commenting out the sigmoid primes to be 1 should have been the same as giving me a cross entropy. Alright, we're gonna skip this verification. Yeah, we're just gonna skip it. I can just believe that that's right. I don't think it's gonna help that much to prove it. Let's return to the toy example we played with earlier and explore what happens when we use the cross entropy instead of the quadratic cost. To reorient ourselves, we'll begin with the case where the quadratic cost did just fine, with starting weight of 0.6 and starting bias of 0.9. Press run to see what happens when we replace the quadratic cost by the cross entropy. I think on first glance it looks about the same as before. Unsurprisingly, the neuron learns perfectly well in this instance, just as it did earlier, and now let's look at the case where the neuron got stuck. And now this does not get stuck, it goes directly down. Success! This time the neuron learned quickly, just as we hoped. If you observe closely, you can see that the slope of the curve was much steeper initially than the initial flat region of the corresponding curve for the quadratic cost. It's that steepness which the cross entropy buys us, preventing us from getting stuck when we'd expect our neuron to learn fastest, i.e. when the neuron starts out badly wrong. I didn't say what learning rate was used in the examples just illustrated. Earlier with the quadratic cost, we used eta equals 0.15. Should we have used the same learning rate in the new examples? In fact, with the change in cost function, it's not possible to say precisely what it means to use the same learning rate. It's an apples and oranges comparison. Oh. For both cost functions, I simply experimented to find a learning rate that made it possible to see what's going on. If you're still curious despite my disavowal, here's the lowdown. I used eta equals 0.005 in the examples just given. Okay, so if we go over here and we change these to be 1, and then we also change the learning rate to be, let's say, 0.3, so 10 times smaller. Now we're learning faster. Okay, let's kill that. Make it 10 times even smaller than that. That didn't really make a change. What if it's 10 times smaller than that? I don't think that's better either. So were we best between 0.3 and let's do a little higher than 0.3 and a little lower than 0.3. So start with 0.5. That's working all right. Let's do 0.1. It's also all right, but not as good. So how about 1.0? That's kind of the same as 0.0 or 0.3, which got us 80 right away and then plateaus around 85. Okay, so I don't know. It still doesn't seem better than the non-cross entropy version with an eta of 3, which was this. jumps directly to 90, I think, and then stays, yeah, and goes up to 95. So maybe there's something else we could tweak, but I don't know, we'll see. You might object that the change in learning rate makes the graphs above meaningless. Who cares how fast the neuron learns when our choice of learning rate was arbitrary to begin with? That objection misses the point. The point is that the point of the graphs isn't about the absolute speed of learning, it's about the speed of learning changes. In particular, when we use the quadratic cost, learning is slower when the neuron is unambiguously wrong than it is later on, as the neuron gets closer to the correct output. While with the cross entropy, learning is faster when the neuron is unambiguously wrong. Those statements don't depend on how the learning rate is set. We've been studying the cross entropy for a single neuron, however it's easy to generalize the cross entropy to many neuron multi-layer networks. In particular, suppose y equals y1, y2, etc. are the desired values at the output neurons, i.e. the neurons in the final layer, while a1, a2, etc. are the actual output values. Then we define the cross entropy by C equals -1 over n, sum over x, sum over j of yj ln a of j, plus 1 minus yj ln 1 minus a of j. This is the same as our earlier expression, equation 57, except now that we've got the summations summing over all the output neurons. I won't explicitly work through a derivation, but it should be plausible that using the expression 63 avoids a learning slowdown in many neuron networks. If you're interested, you can work through the derivation in the problem below. Incidentally, I'm using the term cross-entropy in a way that has confused some early readers since it superficially appears to conflict with other sources. In particular, it's common to define the cross-entropy for two probability distributions, pj and qj, as sum over j of pj ln qj. This definition may be connected to 57. If we treat a single sigmoid neuron as outputting a probability distribution consisting of the neuron's activation A and its complement 1 minus A. However, when we have many sigmoid neurons in the final layer, the vector aj of activations doesn't usually form a probability distribution. As a result, a definition like sum over j of pj ln q J doesn't even make sense since we're not working with a probability distribution. Instead, you can think of 63 as a summed set of per neuron cross entropies, with the activation of each neuron being interpreted as part of a two-element probability distribution. In this sense, 63 is a generalization of the cross entropy for probability distributions. Footnote, of course, in our networks there are no probabilistic elements, so they're not really probabilities. Alright, I didn't really understand that, but I don't think this aside was meant for me because I didn't have that confusion. I'm just taking the cross entropy as a magic formula. When should we use the cross entropy instead of the quadratic cost? In fact, the cross entropy is nearly always the better choice, provided the output neurons are sigmoid neurons. To see why, consider that when we're setting up the network, we usually initialize the weights and biases using some sort of randomization. It may happen that those initial choices result in the network being decisively wrong for some training input. That is, an output neuron will have saturated near 1 when it should be 0 or vice versa. If we're using the quadratic cost, that will slow down learning. It won't stop learning completely since the weights will continue learning from other training inputs, but it's obviously undesirable. Okay. Exercises. One gotcha with the cross entropy is that it can be difficult at first to remember the respective roles of the y's and the a's. It's easy to get confused about whether the right form is negative y ln a plus 1 minus y ln 1 minus a, or negative a ln y plus 1 minus a ln 1 minus y. What happens to the second of these expressions when y equals 0 or 1? Does this problem afflict the first expression, y or y not? So this is the wrong one. Let's try y equals 0. Well, when y equals 0, this is negative infinity. And when y equals 1, this is negative infinity. And I guess the problem doesn't afflict the first expression because our activation will be close to but not exactly equal to 0 or 1, whereas the output will be exactly equal to 0 or 1. So I guess that does clear up a confusion I had earlier. In the single neuron discussion at the start of this section, I argued that the cross entropy is small if sigmoid of z is approximately equal to y for all training inputs. The argument relied on y being equal to either 0 or 1. This is usually true in classification problems, but for other problems, e.g. regression problems, y can sometimes take values intermediate between 0 and 1. Show that the cross entropy is still minimized when sigmoid of z equals y for all training inputs. When this is the case, the cross entropy has the value... Yeah, so they just replaced A with Y in the cross entropy formula. So Y is some value not 0 or 1. So we can't just make part of the expression go away anymore. I don't know. I don't see an obvious way for me to attack this. Maybe I have to know about the binary entropy function. So h of x goes between 0 and 1, and its peak at 1 is at 0.5, and it's 0 at 0 and 1. I don't know how that helps me. I mean, it tells me that this is a number between 0 and 1. I don't know. I don't... I don't know. I don't know, and I'm not sure how to make progress, and I think I'm okay with just saying, yeah, the cross entropy goes down when you're closer to being right. I think I can just accept that. Okay, problems. Many-layer multi-neuron networks. In the notation introduced in the last chapter, show that for the quadratic cost, the partial derivative with respect to the weights in the output layer is quadratic cost, so that's what we were doing here. The partial derivative with respect to the weights in the output layer is so isn't this the isn't this one of the BP equations? I think I need to open up chapter 2 and pull up the BP equations, or possibly they're in chapter 1. Here they are. So derivative of c with respect to w is activation of the last layer times delta of this layer. And they're asking me to prove that that's equal to this thing. So activation of last layer is right here. Delta of this layer, and we're talking about the final layer. So delta of this layer is this. Derivative of c with respect to a, Hadamard product sigmoid prime of z. So here's your sigmoid prime of z, and this is going to be derivative of c with respect to a. The term sigmoid prime ZL causes a learning slowdown whenever an output neuron saturates on the wrong value. Show that for the cross entropy cost, the output error delta L for a single training example X is given by delta equals activation minus Y. Which would have been this, which would have been removing the thing here and putting a 1 here. So yeah, we already know this. We saw that right? We already read that that's what would happen. Do we have an expression for the derivative of the cost function somewhere? Yeah, here. But it's just the same without the sigmoid prime. Use this expression to show that the partial derivative with respect to the weights of the output layer is given by same thing as before, but without the sigmoid prime. The sigmoid prime term has vanished, and so the cross entropy avoids the problem of learning slowdown, not just when used with a single neuron, as we saw earlier, but also in many layer multi-neuron networks. A simple variation of this analysis holds also for the biases. If this is not obvious to you, then you should work through that analysis as well. Okay, using the quadratic cost when we have linear neurons in the output layer. Oh. Oh. Okay. So I kind of want to try this now. All right, what's the right way to do this? I think maybe in the initialization of the network, the thing I want to try is use linear neurons or like almost linear neurons like ReLUs and cross entropy at the same time, because the cool thing about cross entropy is that it avoids the problem that linear neurons like ReLUs have of their having no slope, or like the slope is always positive, or is always 1. What am I trying to say? Sigmoids had a problem where the slope on the ends would be close to 1 or close to 0, which means that you can't learn on the ends. ReLUs don't have that problem. they have a kind of a related problem where you can't learn when you're negative and you can learn when you're positive, and you can always learn the same amount when you're positive. So using ReLUs instead of sigmoids is a different way to get rid of the sigmoid primes here. So yeah, okay. So then what happens if you use ReLUs and or linear neurons and cross entropy at the same time? I'm not sure, and I think the reason I'm not sure is that I don't really know why the sigmoid primes went away when I changed to a cross entropy cost function. But anyway, quadratic cost with linear neurons, my prediction is this is a different way to get rid of the sigmoid primes, to get rid of the learning slowdown at 0 and 1. Suppose that we have a many-layer multi-neuron network. Suppose all the neurons in the final layer are linear neurons, meaning that the sigmoid activation function is not applied, and the outputs are simply A is equal to Z. Show that if we use the quadratic cost function, then the output error delta for a single training example X is given by A minus Y. Yes. So if you use, it's basically because the slope of Z will be 1. So this goes away. So you end up back with this. Similarly to the previous problem, show that this expression shows, use this expression to show that the partial derivatives with respect to the weights and biases in the output layer is given by this. And it's the same thing. It's just you got rid of the derivative because the derivative's 1. This shows that if the output neurons are linear neurons, then the quadratic cost will not give rise to any problems with a learning slowdown. In this case, the quadratic cost is, in fact, an appropriate cost function to use. Okay. So that's a different way to do it. Is to change just one layer. So that would mean to do this basically. So that it only affects the output layer. Yeah, that seems to work okay. It's maybe marginally worse than before. No, it's about the same. 95%, that's about the same as before. Huh. And then we could maybe try to tune the learning rate if I lower it by 10x. It's doing better. It's like jumping around less. It's more consistently increasing. So I think a lowered learning rate makes a bit more sense. Yeah, maybe if it were just a little more than that, let's double it from there. That's looking real good. 95.3%, 95.4%. Yeah. That's the best we've done so far, I think. 95.7% final accuracy. Interesting. So that was by changing the... No, you know what? That was messed up what I just did, because I didn't change the forward propagation. So I wasn't optimizing correctly. What I should have done is removed the sigmoid on the last layer, which I didn't do. So why don't, let me try to implement something that I know I'm gonna need eventually, which is to tell the network what kind of layers each of its things are. So instead of just sizes, you're gonna have to give me a list of tuples where you tell me the size, that as in the number of neurons, and you also tell me the type of neuron. What can I call that? Activation function? Neuron? And do you need to just give me a type? I think you do just need to give me a type. Oops. So let's do class sigmoid is a neuron. Class neuron is nothing. It's just, well, actually, it won't be nothing. It'll be a... Let's use this fancy thing from Python called protocols, which I'm not sure how to use. Python protocol. From typing, import protocol. So a neuron is a protocol that's going to have a f function that takes a number, float, and returns a number. And then, why doesn't it like that? Well, okay, and then f prime also. Instance method should take a self parameter. Fair. Though it doesn't actually, it's actually, these will not be instance methods. These will just be class methods. Or even static methods. Am I allowed to put the 3 dots here? So that's a neuron. A sigmoid looks like this. And then why don't we call these Z, and these should actually be ND array, ND array. So what does it have against this? Am I allowed to reference myself here? No, I am having some problems here, so... Alright, num layers, I don't actually use that, so let's get rid of that. Sizes is going to be the first thing in each tuple. So I'll say, let's call this layers instead of sizes. Sizes equals layer. Layer of 0 for layer in layers. And now these can be self.sizes. Okay. When you apply, you have to use the correct activation function for that layer. So self.layers, and I'm not storing it. Let's call self.layers. But what can I call this? Let's do neurons. So neurons, n, and then don't call sigmoid, call n.f. Okay, what's wrong with this though? The type parameter z must be a supertype of its class sigmoid. Oh, it doesn't know that it's a static method. Let's add static method, static method. Okay. Then where else are we calling sigmoid? This shouldn't be sigmoid, this should be n self dot neurons n dot f. This is not sigmoid prime, this is self.neurons of the last layer dot f prime. And this is not sigmoid prime, this is self.neurons of this layer, which is j dot f prime. Right? Sigmoid prime, yeah. Okay. Now when we call this, the way we want to initialize it is like this. For each of these, it's a tuple where you say something like sigmoid. Can I not join these two together? No. Okay. Does this work? And then if I, yeah. So this should, if I do eta equals 3.0, now it should do the thing where it starts around 90 and then goes to 95. Okay, that looks like it's working. Now let's make the last layer be not sigmoid. We'll just have it be linear. Let's go over to let's clean up our code also a little bit. So this stuff, let's make a, here, let's copy this. Let's make a new file we'll call neurons.py. From typing import protocol from, or import numpy as np. And here you're doing from neurons import neuron. And over here from neurons import sigmoid and linear. Then let's go implement linear. So linear means you just return z, and the derivative of that is just 1. Oh. How do we turn that into an NP array? I wonder if I can just like how would I do this? NumPy array of ones. There's a thing called np.ones. So what if I do return np.ones z.shape? Now, yeah, so now we've got sigmoid, sigmoid, linear. These are actually, well, these are inputs. Like, these aren't, can I just call them, like, it shouldn't matter what I call them because they don't do any, you shouldn't use, what am I trying to say? They shouldn't get used. So if I call this input and I have these just rays, exception, don't call, or this is an input layer. the input layer is not supposed to be having weights and biases. Is it? I don't think it is. Right? I'm doubting myself. Yeah, because we have one less. Okay, so the sizes are these. The neurons, skip the first layer. They don't matter. They're input layers. Okay, how does this do? It's broken now. How did I break it? Interestingly, self.sizes, or sizes is not used elsewhere than right here. So I'm not gonna make this be self.sizes because we don't need to remember them. It's not raising the exceptions. But if I get rid of this, will it start raising exceptions? Yeah. So if I do this, it's at least not raising exceptions, but it's giving the wrong answers for some reason. What if we used only sigmoid? Then would it go back to working? Yes, so there's a problem with my linear neurons. So I'm pretty sure this is right, and I'm guessing there's a problem with this. Like, do I have to unpack this? No. Yeah, it looks like I shouldn't have to unpack it because it's because in the example here it takes a tuple. So f prime this should basically not change the thing. I wonder if neurons of J is the wrong thing to grab here. I think it might need to be J plus 1 actually. Should it? No, because because I don't want to be grabbing the linear layers stuff in here. So Just curious, if this were just 1, which is how it's supposed to be behaving, would it work? No. So the problem's probably in here, so I could just try doing a j+1. That's not working. How about a -1? I don't know why that would work. It shouldn't work. And it doesn't. If this were just a 1, would it give better results? No. Something's messed up. What's wrong? Bunch of overflows, which were not happening when everything was a sigmoid. If you're sigmoid, no overflows, and if you're linear, overflows. Okay. How do I tell this don't stop importing this? If I just do that, will it? Yeah, okay. So I have a guess as to what's going on. And my guess is the output activation is ending up being big, like not between 0 and 1. Which is causing some problems. And I'm guessing that I'm jumping the gun here by trying to implement linear layers, and I'm gonna need some kind of normalization to make that work. Otherwise, stuff can just go to infinity and cause problems. So why don't we be patient and see if we can come back to this. This shows that if the output neurons are linear neurons, then the quadratic cost will not give rise to any problems with a learning slowdown. In this case, the quadratic cost is in fact an appropriate cost function to use. Okay. Okay, back to reading, because I don't know how I can fix the problem. I don't know how to normalize the activations of the output layer. Is that what I would want to do? Because I guess I could just rescale them to be between 0 and 1. But is that what would be causing the overflows? What if I tried doing that? So instead of returning z, you returned z but scaled. Is there like a dot scale? No. Z divided by z dot argmax. I'm not using the linear neurons. No, that doesn't work. Okay, I don't know yet. We'll have to come back to that. Using the cross entropy to classify MNIST digits. The cross entropy is easy to implement as part of a program which learns using gradient descent and backpropagation. We'll do that later in the chapter, developing an improved version of our earlier program for classifying the MNIST handwritten digits, network.py. The new program is called network2.py and incorporates not just the cross entropy, but also several other techniques developed in this chapter. Footnote. Code's available on GitHub. For now, let's look at how well our new program classifies MNIST digits. As was the case in Chapter 1, we'll use a network with 30 hidden neurons, and we'll use a mini batch size of 10. We set the learning rate of eta equals 0.5, and we train for 30 epochs. The interface to network2.py is slightly different than network.py, but it should still be clear what's going on. You can, by the way, get documentation about network2.py's interface by using commands such as help network2.network.sgd in a Python shell. So cost is a function that's getting passed in here. Asterisks, or footnote. In Chapter 1, we used the quadratic cost and a learning rate of eta equals 3.0. As discussed above, it's not possible to say precisely what it means to use the same learning rate for when the cost function is changed. For both cost functions, I experimented to find a learning rate that provides near optimal performance given the other hyperparameter choices. There is, incidentally, a very rough general heuristic for relating the learning rate for the cross entropy and the quadratic cost. As we saw earlier, the gradient terms for the quadratic cost have an extra sigmoid prime equals sigmoid times 1 minus sigmoid term in them. Suppose we average this over values for sigmoid. Integral from 0 to 1 of d sigmoid times sigmoid of 1 minus sigmoid equals 1 over 6. We see that very roughly the quadratic cost learns an average of 6 times slower for the same learning rate. This suggests that a reasonable starting point is to divide the learning rate for the quadratic cost by 6. Of course, this argument is far from rigorous and shouldn't be taken too seriously. Still, it can sometimes be a useful starting point. What do we divide by 6? The quadratic cost learns 6 times slower than the cross entropies. So if you're going from one to the other, you multiply by 6 or you divide by 6. Okay. So there's a bunch of stuff in here that I don't really want to know about until I can learn it myself and initialize it myself, or implement it myself. Note, by the way, that net.largeWeight initializer command is used to initialize the weights and biases in the same way as described in chapter 1. We need to run this command because later in the chapter we'll change the default weight initialization in our networks. The result from running the above sequence of commands is a network with 95.49% accuracy. This is pretty close to the result we obtained in chapter 1, 95.42% using the quadratic cost. So the funny thing is, using cross entropy, like, how do you pass cross entropy as a parameter? Because it seems to me like the effect of using cross entropy is that this term goes away. But that would also be the case if you switch the last layer to be linear. Interesting. Let's look at the case. Let's also look at the case where we use 100 hidden neurons, the cross entropy, and otherwise keep the parameters the same. In this case, we obtain an accuracy of 96.82%. That's a substantial improvement over the result from chapter 1, where we obtained a classification accuracy of 96.59% using the quadratic cost. This may look like a small change, but consider that the error rate has dropped from 3.41% to 3.18%. That is, we've eliminated about 1 in 14 of the original errors. That's quite a handy improvement. It's encouraging that the cross entropy cost gives us similar or better results than the quadratic cost. However, these results don't conclusively prove that the cross entropy is a better choice. The reason that I've put only a little effort into choosing hyperparameters such as the learning rate, mini batch size, and so on for the improvement to be really convincing, we'd need to do a thorough job optimizing such hyperparameters. Still, the results are encouraging and reinforce our earlier theoretical arguments that the cross entropy is a better choice than the quadratic cost. This, by the way, is part of a general pattern that we'll see through this chapter, and indeed through much of the rest of the book. We'll develop a new technique, we'll try it out, we'll get improved results. It is, of course, nice that we see such improvements, but the interpretation of such improvements is always problematic. They're only truly convincing if we see an improvement after putting tremendous effort into optimizing all other hyperparameters. That's a great deal of work, requiring lots of computing power, and we're not usually going to do such an exhaustive investigation. Instead, we'll proceed on the basis of informal tests like those done above. Still, you should keep in mind that such tests fall short of definitive proof and remain alert to signs that the arguments are breaking down. By now, we've discussed the cross entropy at great length. Why go to so much effort when it gives only a small improvement to our MNIST results? Later in the chapter, we'll see other techniques, notably regularization, which give much bigger improvements. So why so much focus on cross entropy? Part of the reason is that the cross entropy is a widely used cost function and so is worth understanding well, but the more important reason is that neuron saturation is an important problem in neural nets, a problem we'll return to repeatedly throughout the book, and so I've discussed the cross entropy at length because it's a good laboratory to begin understanding neuron saturation and how it may be addressed. Okay, I actually do want to take a peek at his code to understand how cost can be an argument. So let's figure that out. Cost. So quadratic cost has the regular function, which is this, which you don't actually use, I don't think. And then the delta. Oh, he baked in sigmoid prime to the cost function. That's the thing I didn't understand, is how do you bake in, or how do you write the cost function in a way where it doesn't care what your layer is? But you don't, it looks like. And then I don't think you actually use fn. Oh, you do if you're trying to calculate the cost, but I don't think that is actually used. It's only used when for debugging. Okay. All right. What does the cross entropy mean? Where does it come from? Our discussion of the cross entropy has focused on algebraic analysis and practical implementation. That's useful, but it leaves unanswered broader conceptual questions like, what does the cross entropy mean? Is there some intuitive way of thinking about the cross entropy? And how could we have dreamed up the cross entropy in the first place? Let's begin with the last of these questions. What could have motivated us to think up the cross entropy in the first place? Suppose we discovered the learning slowdown described earlier and understood that the origin was the sigmoid prime of z terms in equations 55 and 56. After staring at those equations for a bit, we might wonder if it's possible to choose a cost function so that the sigmoid prime of z term disappeared. In that case, the cost c equals cx for a single training example would satisfy these relationships. If we could choose the cost function to make those equations true, then they would capture in a simple way the intuition that the greater the initial error, the faster the neurons learn. They'd also eliminate the problem of a learning slowdown. In fact, starting from these equations, we'll now show that it's possible to derive the form of the cross entropy simply by following our mathematical noses. To see this, note that from the chain rule we have this. Using sigmoid prime of z equals sigmoid of z times 1 minus sigmoid of z equals a times a minus 1, the last equation becomes derivative of c with respect to b equals derivative of c with respect to a times 1 minus a. Comparing to equation 72, which is the equation we want it to be, we obtain a minus y over a times 1 minus a. Integrating this expression, we get the cross entropy for some constant of integration. This is the contribution to the cost from a single training example x. To get the full cost function, we must average over training examples, obtaining this, where the constant here is the average of the individual constants for each training example. And so we see that equations 71 and 72 uniquely determine the form of the cross entropy, up to an overall constant term. The cross entropy isn't something that was miraculously pulled out of thin air. Rather, it's something we could have discovered in a simple and natural way. What about the intuitive meaning of the cross entropy? How should we think about it? Explaining this in depth would take us further afield than I want to go. However, it is worth mentioning that there is a standard way of interpreting the cross entropy that comes from the field of information theory. Roughly speaking, the idea is that the cross entropy is a measure of surprise. In particular, our neuron is trying to compute the function x goes to y equals y of x, but instead it computes the function x goes to a equals a of x. Suppose we think of a as our neuron's estimated probability that y is 1, and 1 minus a is the estimated probability that the right value for y is 0. Then the cross entropy measures how surprised we are on average when we learn the true value for y. We get low surprise if the output is what we expect, and high surprise if the output is unexpected. Of course, I haven't said exactly what surprise means, and so this perhaps seems like empty verbiage, but in fact, there is a precise information theoretic way of saying what is meant by surprise. Unfortunately, I don't know of a good, short, self-contained discussion of this subject that's available online, but if you want to dig deeper, then Wikipedia contains a brief summary that will get you started down the right track. And the details can be filled in by working through the materials about the Kraft inequality in Chapter 5 of the book about information theory by Cover and Thomas. Problem: we've discussed at length the learning slowdown that can occur when output neurons saturate in networks using the quadratic cost to train. Another factor that may inhibit learning is the presence of the xj term in equation 61. Because of this term, when an input xj is near to 0, the corresponding weight wj will learn slowly. Explain why it is not possible to eliminate the xj term through a clever choice of cost function. I don't know. I don't know. I'd have to get into the math. I'd have to see how this was derived and figure out where the x is coming from. And I don't really want to do that, honestly. I'm not trying to get deep into the math. I'm just trying to build an LLM. I'm just trying to learn what I need to do that. So I'm interested in doing my own implementations. I'm not interested in understanding all of the math. Okay, Softmax. And I know this is used in practice, so we're going to pay attention and we're going to try to implement this. In this chapter, we'll mostly use the cross-entropy cost to address the problem of a learning slowdown. However, I want to briefly describe another approach to the problem based on what are called Softmax layers of neurons. We're not actually going to use Softmax layers in the remainder of the chapter. I will, so if you're in a great hurry, you can skip to the next section. However, Softmax is still worth understanding, in part because it's intrinsically interesting, and in part because we'll use Softmax layers in chapter 6 in our discussion of deep neural networks. The idea of Softmax is to define a new type of output layer for our neural networks. It begins in the same way as with the sigmoid layer by forming the weighted inputs. Z equals sum over A's plus B's. Footnote, in describing the Softmax, we'll make frequent use of notation introduced in the last chapter. You may wish to revisit that chapter if you need to refresh your memory about the meaning of the notation. Nope. However, we don't apply the sigmoid function to get the output. Instead, in a Softmax layer, we apply the so-called Softmax function to Z. According to this function, the activation A of the jth output neuron is e to the z over sum of e to the z's, where in the denominator we sum over all the output neurons. If you're not familiar with the Softmax function, the equation 78 may look pretty opaque. It's certainly not obvious why we'd want to use this function, and it's also not obvious that this will help us address the learning slowdown problem. To better understand equation 78, suppose we have a network with 4 output neurons and 4 corresponding weighted inputs, which will denote Z1, Z2, Z3, and Z4. Shown below are adjustable sliders showing possible values for the weighted inputs and a graph of the corresponding output activations. A good place to start exploring is by using the bottom slider to increase Z4. This is the Softmax. Okay. So I get the intuition of the Softmax. It's kind of like a continuous argmax. So it'll take the biggest thing and make it even bigger, and it'll take all the things that aren't as big and make them even smaller, but in a continuous way. That's my understanding of Softmax. As you increase Z4, you'll see an increase in the corresponding output activation A4 and a decrease in the other output activations. Similarly, if you decrease Z4, then AA4 will decrease, and all the other output activations will increase. In fact, if you look closely, you'll see that in both cases, the total change in the other activations exactly compensates for the change in A4. The reason is that the output activations are guaranteed to always sum up to 1, as we can prove using equation 78 and a little algebra. Sum over the AJs is equal to here, let's open up equation 78. So the value at AJ is equal to e to the z of j divided by the sum of e to the z of everything else. Or not everything else, everything including j. So the bottom term is the same for all of them. Yeah, so when you sum up all the AJs, you get the same top term and the same bottom term, which equals 1. As a result, if A4 increases, then the other output activations must decrease by the same total amount to ensure the sum over all activations remains 1. And of course, similar statements hold for all the other activations. Equation 78 also implies that the output activations are all positive since the exponential function is positive. Combining this with the observation in the last paragraph, we see that the output from the softmax layer is a set of positive numbers which sum to 1. In other words, the output from the softmax layer can be thought of as a probability distribution. This is what I was trying to get at earlier when I was saying, like, I need to rescale the linear layer. So if I add let's add a softmax layer. Softmax. I don't know what its derivative is, but this is the, and I'm guessing I can probably do np.softmax. No. What about z.softmax? No? Huh. Okay, well I can just do it myself. np.exp. Because the denominator is the sum of taking the exponential on everything. What's wrong with this? Int not assignable to return type. Okay, yeah. This is the denominator. And then the numerator is you take the exp of each thing. Whoa, this isn't f prime. This is f. The fact that a softmax layer outputs a probability distribution is rather pleasing. In many problems, it's convenient to be able to interpret the output activation. Actually, I can figure out f prime, right? It's because I guess this is not a constant. It's almost a constant. Because it's going to be like the same thing, because the exponential is its own derivative. It might literally be exactly the same, because these will also be their own derivatives. I'm just not 100% sure how this factor gets derived, but let's see. The fact that a softmax layer outputs a probability distribution is rather pleasing. In many problems, it's convenient to be able to interpret the output activation A of j as the network's estimate of the probability that the correct output is j. So for instance, in the MNIST classification problem, we can interpret A of j as the network's estimated probability that the correct digit classification is j. Can I try running this with a softmax? Nah, it's messed up. Okay. Why though? We're getting weird overflows that I can't deal with, and I'm not sure why they're happening. What does X2 mean? I wonder. Whatever. Okay. By contrast, if the output layer was a sigmoid layer, then we certainly couldn't assume that the activations formed a probability distribution. I won't explicitly prove it, but it should be plausible that activations from a sigmoid layer won't in general form a probability distribution. And so with a sigmoid output layer, we don't have such a simple interpretation of the output activations. Exercise could show that this last statement is true. I don't want to do this exercise. It seems obvious. It's like, why would it, basically? And also, we've seen examples before where it wasn't. We're starting to build up some feel for the Softmax function and the way the Softmax layers behave. Just to review where we're at, the exponentials in equation 78 ensure that all the output activations are positive, and the sum in the denominator of equation 78 ensures that the Softmax outputs sum to 1. So that particular form no longer appears so mysterious. Rather, it is a natural way to ensure that the output activations form a probability distribution. You can think of a softmax as a way of rescaling the ZJs and then squishing them together to form a probability distribution. Exercises. Monotonicity of softmax. Show that the derivative of AJ with respect to ZJ is positive if J equals K and negative if J equals not K. As a consequence, increasing Z of J is guaranteed to increase the corresponding output activation AJ and will decrease all other output activations. We already saw this empirically with the slider, but this is a rigorous proof. So I'm not super interested in rigorous proofs, but I think this is kind of easy to do. So show that the derivative of this is positive on the component that we're looking at, or the derivative with respect to this component is positive, and the derivative with respect to the other components is negative. I mean, I guess it's kind of obvious. If you increase the jth component, then the thing will go up, because that's the numerator. If you increase a different component, the thing will go down, because that's the denominator. I guess it'll go down because that's the denominator. If you increase the component that of J, that's in the numerator and the denominator. But it's more in the numerator than in the denominator, if that makes sense. Because the denominator is has these other terms in it. So it increases the numerator and the denominator by the same amount, but the denominator is already bigger than the numerator, so you're proportionally increasing the numerator more. Okay, that's rigorous enough for me. Non-locality of softmax. A nice thing about sigmoid layers is that the output AJ is a function of the corresponding weighted input, aj equals sigmoid of z, j. Explain why this is not the case for a softmax layer. Any particular output activation aj depends on all the weighted inputs. Yeah, because they're in the denominator for each component, that's why. Inverting the softmax layer. Suppose we have a neural network with a softmax output layer, and the activations aj are known. Show that the corresponding weighted inputs have the form zj equals ln of a plus c for some constant c that is independent of j. Well, if you're taking the opposite of the exponential, so you're getting the logarithm. And then the division is harder to reason about. I guess you could call the c a constant in that it's independent of j, because it's the same for all of the j's. It's not independent of a, so it's weird to call it a constant, but it is independent of j. The learning slowdown problem. We've now built up considerable familiarity with softmax layers of neurons, but we haven't yet seen how a softmax layer lets us address the learning slowdown problem. To understand that, we'll define the log likelihood cost function. Okay, so we also needed to swap the cost function. We'll use x to denote a training input to the network and y to denote the corresponding desired output. The log likelihood cost associated to this training input is defined as c is defined as negative ln of a. So for instance, if we're training with MNIST images and input an image of a 7, then the log likelihood of the cost is ln of a7. To see that this makes intuitive sense, consider the case where the network is doing a good job. That is, it is confident the input is a 7. In that case, it will estimate the value for the corresponding probability a7 of L, which is close to 1, and so the cost negative ln of a7L will be small. By contrast, when the network isn't doing such a good job, the probability a7L will be smaller, and the cost ln of a7 will be larger. So the log likelihood cost behaves as we'd expect a cost function to behave. What about the learning slowdown problem? To analyze that, recall that the key to the learning slowdown is the behavior of the quantities derivative of c with respect to wjk and derivative of c with respect to bj. I won't go through the derivation explicitly, I'll ask you to do that in the problems below, and I probably won't do it either. But with a little algebra, you can show that derivative of c with respect to b is a minus y. Derivative c with respect to w is a of the last layer times a of the previous layer times a of this layer. This layer being the last layer minus y. Footnote, note that I'm abusing notation here, using y in a slightly different way to last paragraph. In the last paragraph, we used y to denote the desired output from the network, e.g. output of 7 if an image of a 7 was input, but in the equations which follow, I'm using y to denote the vector of output activations which correspond to a 7. That is, a vector which is all zeros except for a 1 in the 7th location. These equations are the same as the analogous expressions obtained in our earlier analysis of cross entropy. Compare, for example, equation 82 to equation 67. It's the same equation, albeit in the latter I've averaged over training instances. And just as in the earlier analysis, these expressions ensure that we will not encounter learning slowdown. In fact, it's useful to think of a softmax output layer with a log likelihood cost as being quite similar to a sigmoid output layer with a cross entropy cost. So it's basically like if I just lied and said it was a 1, I would get the right answer, basically, right? Like, this is not actually the correct derivative, but this is now going to act as though it's a softmax with a log likelihood. Which is really weird to think about, and it's working well. And it could probably work better if I tweaked the learning rate. I think the learning rate should be a little smaller because I saw it bouncing around a little. So let's make it 10 times smaller. Maybe it needs to be a little higher than that. This is pretty good, though now it's starting to go down. Yeah, that's quite good. Yeah, it's just weird that my layers and like this is also weird. Like why doesn't my linear work? I didn't try doing this, literally returning a 1 instead of a vector of 1s. This has less of a problem, interestingly. But yeah, linear doesn't really make sense, I think. Though what does make sense would be well, okay. Like here's what I want to try, but it's not really gonna work. Let's do a rectified linear unit. This returns max of 0 and z, which doesn't make sense when I do it like that. I have to do it in a component-wise way. So z dot apply component wise numpy. Custom component wise numpy. So I can call, oh, no, I don't want to use numba. I don't know what that is. What's reduction OP? Oh, that's like... Well then what? Oh, okay, hold on. This is a little hard to read. Yeah, this is what I want. So I can just do numpy.vectorize. Numpy vectorize. Okay. np.vectorize lambda x is going to be the max of 0 and x, and we're going to apply that to z. No. This is the operation. And then you apply that to z, like that. Then f prime is basically 1 everywhere that f is greater than 0 and 0 elsewhere. So we can do the same vectorization thing. One if x greater than 0, else 0. And can we try having an inner ReLU layer instead of an inner sigmoid layer? It was working for a second, and then it invalid value encountered in divide. Interesting. Is there a safer way to do softmax? NumPy softmax. Why are we shifting X? It almost makes sense to me. Keep dims default true? I don't know. Does this help? Does this help us not divide by 0, basically? No, it immediately had the same problem. But what was the problem? Overflow. And then it didn't like the subtraction. Okay, let's go back to how we were doing it. Does NumPy sum do any better than Python sum? No. Invalid value encountered in lambda vectorized. Huh. Does that mean the problem might just be with the way I'm vectorizing? We're getting overflows in exp. So, does this prevent the overflows, at least? Invalid value encountered in subtract, but that was only after we got an overflow in matmul. Okay, I have a different theory. We'll have to come back to these. Still, so far, sigmoid's the only thing that works. I have a different theory now, which is that the matrix, the starting matrix is not a good starting point. Oh, what's going on here? Why is this barely learning anymore? Is it because this Softmax is bad? If I go back to this one, it'll work. No. I thought I had Softmax working a minute ago. What have I changed? I did change to NumPy sum instead of Python sum. Could that be an issue? It is an issue. Wow, interesting. Okay, and then one other weird thing. Sigmoid cross entropy output is going to be this. So if we go here, this should work hopefully, and it should be the same as passing in a different cost function. Cool. Okay. Given this similarity, should you use a sigmoid output layer in cross entropy or a softmax output layer and log likelihood? Oh, I guess I should be explicit about that. Softmax. Oh, I already did that. Log likelihood. In fact, in many situations, both approaches work well. Through the remainder of this chapter, we'll use a sigmoid output layer with the cross entropy cost. Later in chapter 6, we'll sometimes use a softmax output layer with log likelihood cost. The reason for the switch is to make some of our later networks more similar to networks found in certain influential academic papers. As a more general point of principle, softmax plus log likelihood is worth using whenever you want to interpret the output activations as probabilities. That's not always a concern, but can be useful with classification problems like MNIST involving disjoint classes. Problems. Derive equations 81 and 82. No, thank you. Where does the softmax name come from? Suppose we change the softmax function so that the output activations are given by e to the cz, where c is a positive constant. Note that c equals 1 corresponds to the standard softmax function, but if we use a different value of c, we get a different function, which is nonetheless qualitatively rather similar to the softmax. In particular, show that the output activations form a probability distribution, just as for the usual softmax. Suppose we allowed c to become larger, i.e. c tends to infinity. What is the limiting value for the output activations a, j? After solving this problem, it should be clear to you why we think of c equals 1 function as a softened version of the maximum function. This is the origin of the term softmax. So as c goes to infinity, I'm guessing this will turn into a max, where whichever the largest contributor is going to be equal to 1, and all the others will be equal to 0. And that's good enough for me. I don't need a rigorous proof, I just want intuition. Backpropagation of a softmax and the log likelihood cost. In the last chapter, we derived the backpropagation algorithm for a network containing sigmoid layers. To apply the algorithm to a network with a softmax layer, we need to figure out an expression for the error. Delta j is defined as derivative of c with respect to zj in the final layer. Show that a suitable expression is delta j equals aj minus yj. Using this expression, we can apply the backpropagation algorithm to a network using a softmax output layer and the log likelihood cost. I thought we already did that. That's how I was able to do this. I guess we did it for, we skipped delta. I just assumed that it was going to be the same. Well, I'm going to leave it there. I don't need to prove those things. I'm happy to just know that they're true. And why don't we stop there and we'll get to overfitting and regularization next time. I think... No, actually, never mind. The thing that's... my theory is that the thing that's going to let me switch to using different neurons is the initializing of the weights and biases. I think that's the thing that's causing our initial Z's to be too big, and so our network gets out of control. Like the values of get out of control and start overflowing when we pass them into functions like e to the negative z. Or not e to the negative z is the one thing that's working, but like exp for the softmax is having problems, and x itself for the ReLU is having problems. All right, so let's end it there.